Hey, welcome! So today, we're going to tackle a question that seems, well, almost like a riddle. We live on a planet that's absolutely covered in water, so why on earth are we talking about a global water crisis? And the big follow-up question is, can science actually give us a way to drink the ocean? Let's dive right in.
I mean, it's a totally fair question, right? You look at any picture of Earth from space, and it's just this big, beautiful, blue marble. But you know, that blue is a little bit deceiving. The truth is, the huge, vast majority of all that water is completely useless to us as drinking water.
And yeah, there it is. That's the catch. More than 97% of all the water on our planet is salt water, locked away in the oceans. So getting that salt out, the process we call desalination, is, and I'm not exaggerating here, one of the biggest engineering challenges we face. To really get how we do it, we first have to understand a really fundamental force of nature. Okay, so that force is called osmosis. Imagine you separate fresh water from salt water with a special kind of filter. It's called a semi-permeable membrane. You know what happens? The fresh water will naturally flow towards the salty side. It's almost like nature is trying to dilute the saltier water to balance things out. It's a totally natural, one-way street. But for our goal, it's going the completely wrong way. So how in the world do we reverse it? Well, basically, we fight nature with brute force. By applying a whole lot of pressure to the saltwater side, we can literally reverse that natural flow of osmosis. We just push the water molecules through that very same membrane, but this time, the salt and all the other gunk gets left behind. And that is reverse osmosis, or RO for short. It's the core technology that makes modern desalination work.
A modern desalination plant is a pretty complex multi-stage operation. First, you've got the intake and pretreatment. This is where seawater gets sucked in and filtered to get all the big stuff out. You know, sand, seaweed, that kind of thing. Then comes the main event, the high-pressure pumps that force the water through the RO stage. And finally, the water that comes out is super pure, so it goes through post-treatment to add back some minerals and make it safe to drink before it heads out to our taps. But really, the absolute hero of this entire story is the membrane itself. And it's not just any old filter. It's an incredible piece of material science called a thin-film composite membrane, or TFC. This little thing is what makes large-scale, efficient desalination even possible. And this material, it's just amazing. TFC membranes are truly the gold standard in the industry. They have this active layer made of polyamide that's only about 100 nanometers thick. To put that in perspective, that's like 1,000 times thinner than a single human hair. This ridiculously thin layer is the key, and it's so effective that it rejects over 99.5% of the salt while letting those pure water molecules slip right on through. Now, thanks to incredible innovations like the TFC membrane and some clever energy recovery gadgets, the energy cost of desalination has just plummeted. Back in the 70s, it took a whopping 15 to 20 kilowatt hours to produce just 1 cubic meter of fresh water. Today, our best plants have rustled that number all the way down to around 2. It is a fantastic story of engineering progress. But have we hit a wall? And the answer is, yeah, kinda. And that wall is called physics. The laws of thermodynamics actually tell us the absolute bare minimum amount of energy you need to separate salt from water. For your typical seawater, that hard physical limit is 1.06 kilowatt hours per cubic meter. You literally cannot do it for less energy than that, period.
So think about what this means. Our best technology, running at about 2 kilowatt hours, is already bumping right up against that theoretical limit of 1.60. This is a huge deal. It tells us that just making a membrane that lets water through faster isn't going to dramatically lower our energy costs. We are already incredibly close to the best we can ever do with this process. The easy wins on energy efficiency, they're mostly in the past.
So, if a faster filter isn't the magic bullet, where do we go from here? Well, it means we have to turn our attention to the other massive, nagging problem in desalination, a problem that plagues every single plant out there, fouling, or, to use a less scientific term, gunk.
This gunk basically comes in 3 main flavors. First, you've got organic fouling, which is just dissolved stuff from the ocean sticking to the membrane. Then there's scaling. That's when minerals start to build up, kind of like the lime scale you see in an old kettle. And then there's the worst one of all, biofouling. That's when tiny little microorganisms decide the membrane is a great place to live and start growing a slimy biofilm all over it. All of this stuff clogs up the works, makes the plant less efficient, and means they have to do frequent, expensive, and pretty harsh chemical cleanings.
And a really important paper from 2016 just nails the core issue here. It says that for decades, we've basically been improving membranes through trial and error, not through intentional molecular-level design. So to get past this fouling problem and our other limits, we need a totally new way of thinking. We need to build the perfect filter from the molecule up. And where do we look for inspiration for that?
We look to nature, of course. Inside the cells of pretty much every living thing on this planet, from a tiny bacterium to a giant tree to you and me, is the perfect water filter. It's a protein called aquaporin, and it's basically what billions of years of evolution came up with to solve the problem of moving water.
Aquaporin is it's breathtakingly elegant. It's a protein that forms this perfect tiny channel with a sort of hourglass shape. At its narrowest point, it is only 0.28 nanometers wide. That is just barely big enough for a single water molecule to pass through. This tiny little choke point acts as a perfect molecular sieve. Water molecules line up and zip through in single file at incredible speeds, while literally everything else, salts, minerals, even tiny pollutants like boron, is physically blocked from getting through. It has perfect selectivity and unbelievable speed. It's the ultimate blueprint.
So you can see what the billion-dollar question for material scientists is, right? How do we build our own synthetic version of aquaporin? How can we possibly create a membrane that mimics this incredible natural performance, but is also tough enough to survive the brutal, high-pressure world of a desalination plant?
Well, to do this, researchers are looking at some seriously cool next-generation materials. We're talking about things like carbon nanotubes, which are like these perfectly smooth, hollow straws that water can just fly through. Or graphene frameworks, where you take single-atom-thick sheets of carbon and stack them to create perfect little channels. There are even these things called self-assembling polymers. These are smart materials that are designed to automatically form perfectly uniform, nanoscale pores all by themselves.
And this brings us to a really important shift in the goal here. It's not just about making a filter that's more permeable, a faster filter. We've already seen that the energy benefit for that is pretty limited. The real goal now, the holy grail, is to build a smarter filter, a membrane that's designed from the molecule up to solve all the other big problems in the system.
Because if you look at where all the energy actually goes in a modern plant, you see something interesting. The reverse osmosis part itself, that's only about half the story, maybe 55%. A huge chunk of the energy pie is spent on pre-treatment to stop that fouling problem. And another chunk is spent on post-treatment to get rid of the tricky stuff the membrane missed, like boron.
So just imagine the impact of one of these smarter membranes. If you had one that was just naturally resistant to fouling, you could slash the amount of energy and chemicals you use for pre-treatment. If you had one that was resistant to chlorine, it would make getting rid of that bioslime way easier. And if you had one that was super selective, just like aquaporin, it could get rid of tricky pollutants like boron in a single step, completely eliminating the need for expensive post-treatment.
So when we talk about the future of drinking the ocean, it's really not just about pushing water harder through a slightly better filter anymore. It's about building a smarter, more integrated, and more efficient system, starting right down at the molecular level. And that really prompts a much bigger question for all of us. How can we use this kind of molecular-level design not just to solve our water crisis, but to build a more sustainable world for everyone?